Okay, so let's get started now that everyone is suitably caffeinated. Okay, so where did we leave off? We had this statement that the circle epsilon average of H has variance like log of epsilon. So, you know, when that happens, right, the typical value is like the standard deviation. So H of epsilon tends to be order of magnitude, like square root of log epsilon. So most of the time, this quantity over here, e to the gamma H epsilon z, this is not going to be big enough to offset epsilon gamma squared over 2 being really small. Most of the time, this is just going to be very close to 0. Once epsilon is large, then this quantity is small with high probability. On the other hand, this from how Gaussians work, right? If you have n0 epsilon, no, n0 sigma squared random variable, you know, the expected value of that quantity is like e to the sigma squared over 2. And so this is actually just going to be constant order, right? This exponent is a Gaussian with variance negative gamma log epsilon, and so the expected value is like, you know, the reciprocal of this thing. So this quantity is constant order. So, okay. So using that observation, you know, this definition of Gaussian multiplicative chaos maybe makes a bit of sense. So what is Gaussian multiplicative chaos? We want to define a measure which corresponds to the exponential of the Gaussian free field. Okay, so we're going to fix a parameter gamma between 0 and 2, and we define this quantity, this measure over here, a gamma h dz. So at scale epsilon, this is just going to be the Euclidean area measure, and then you weight by e to the gamma h epsilon z. So this is a regularization of e to the Gaussian free field. And you put this renormalization term in front of it. So from what we discussed here, you know, this epsilon to the gamma squared over 2 is a natural choice for the renormalization term. It keeps everything, you know, having a typical size. And the result is that when you send epsilon to 0, this does converge to a non-trivial measure when gamma is between 0 and 2. And this measure is what we call Gaussian multiplicative chaos. So simulations. And this over here is the Gaussian free field we discussed on the previous slide. And over here, what we have done is we've done a dyadic subdivision of the unit square. So you start with the unit square and some threshold, let's say delta. If the total area of the unit square is bigger than delta, you cut into 4 squares. For each of these squares, if the area is bigger than delta, you cut into 4. You keep going and you stop, you know, once all your squares have area roughly equal to delta. And this is what you get. So for this measure A gamma h, for this Gaussian multiplicative chaos measure, each of these dyadic squares has roughly the same area. Okay, so even though this is a large Euclidean area, the GMC area is just like 4 delta. Okay, so this should make some sense when you compare the two pictures. Here, where your geometry is very dense, you have a lot of area, and that corresponds to places where your free field takes very large values. And here, where the values are very small, your GMC area is also very small. Okay, so this is a visualization of the Gaussian multiplicative chaos measure.
Sorry, why it's not subdivided everywhere?
Yeah, so that you stop the subdivision at each square whose area is less than delta with respect to this GMC measure. Yeah. Yeah. Are there any other questions? Okay, so this is a GMC simulation. And from what we discussed earlier, we did say that most of the time the value of e to the gamma h should be kind of small. It should be so small that even when you put this epsilon to the gamma squared over 2, the quantity should be small. And what it translates to is that your measure should be supported on a very small set of points. For a capital point chosen at random from the big measure on the unit square, you should observe that it is not a gamma thick. That the GM's, this e epsilon to the gamma squared over 2, e to the gamma h epsilon z, this should not be large. So it turns out the measure is supported on the so-called gamma thick points of, not this thing. Where did I put the thing? Here. Okay, we're going to close that. Let's shut off the Wi-Fi too. Perfect. So where were we? We're looking at this measure AH gamma, and it turns out it's supported on a fractal set of points called the gamma thick points. So the thickness of a point is defined as follows. We take h epsilon z and we divide by log 1 over epsilon. Take a limit as epsilon tends to 0. That's fine, yeah. For points that satisfy this, we call them alpha thick points. And so this A gamma H measure is supported on points which are gamma thick. Okay. Okay, maybe we should do a few more slides and then I'll move back to the blackboard. I think they're going to switch it on. Okay, but in the meantime, so we can talk about this while the slides are coming on. So this is an example of what we call a random planar map. So what is a planar map? Well, it's a combinatorial object, right? So on the left-hand side, you have a division of the Riemann sphere into triangles. Each of the triangles is colored a different color here. And it's a combinatorial object. Just as how you might draw a graph in two slightly different ways, you don't care about the exact way you draw the graph. In the same way, these combinatorial objects, we view them as being unique only up to homeomorphisms of the Riemann sphere. So this object on the left, we identify with this object on the right. So that's what we call a planar map. It's just a combinatorial way to arrange triangles with the sphere topology. Okay, so there's combinatorially many planar maps with n faces, but it's a finite number, so you can sample one of them at random. Okay, you fix n, very large, you sample a planar map, and what does it look like? So this is a random planar map simulation. The choice of embedding here is the string embedding in an R3. So that means that for every vertex you put an electron on the vertex and a spring on every edge. So the electrons push themselves apart, but the springs keep everything from flying off to infinity. And it kind of bounces around and settles into some kind of stable configuration like the one you see here. So this is an example of a spring-embedded random planar map in R3. This is a different picture, a different model of a random planar map. 3D printed, you can take a look at it after the talk. So, okay. So this is a very cute simulation, but for the purposes of this talk, to relate things to Liouville quantum gravity, we want to embed this combinatorial object inside the unit disk. Right, so a planar map is combinatorial. It doesn't have an intrinsic geometry. So what we're going to do is give it some kind of geometry here. So this is something called a harmonic embedding. The way it's defined is as follows. We sample one of the vertices from the counting measure of the random planar map, and that point is going to become our origin of the unit disk. then we're going to place the boundary vertices of the map. This is a map with the disk topology. You place the boundary vertices on the unit circle in a certain way that I'm not going to describe. And then once that's done, the location of all the other points, you're going to ask for each point to be the average of its neighbor's coordinates. Okay, so the point we chose to be the origin might no longer be the origin once you do this. So each point is just the average of its neighbor's coordinates, and so this is called a harmonic embedding. So this is one way to give a discrete combinatorial object a conformal structure and an embedding inside a unit disk. It turns out that the scaling limit of this random geometry is Liouville quantum gravity, and let me make that more precise. So we have a random planar map with n faces, conformally embedded inside a unit disk. This endows the unit disk with a geometry, right? We can define this area measure on the disk by taking counting measure on the set of vertices and rescaling by some power of n. So that gives us a discrete area measure an. You can define a length measure ln as well by taking the boundary vertices, the counting measure on the boundary, and rescaling by some power of n. And you can also define a graph distance dn. So for any 2 points inside a unit disk, you first go from a point to its nearest vertex, and you look at the graph distance on the graph, and that's going to define dn, the metric, the 2-point distance function. It turns out that this discrete tuple an, ln, and dn converges to a continuum tuple, which you can define using the Gaussian free field. So this first quantity, we've already seen this. This is the Gaussian multiplicative chaos on the unit disk with parameter gamma. This boundary measure here is going to be a boundary version of the Gaussian multiplicative chaos for the free field. And this is something else which we're not going to discuss today. But it's a function of the free field. Okay. So this is one reason math people care about Liouville quantum gravity, because it describes the scaling limits of natural combinatorial objects. It's an important open problem in general to prove this kind of convergence statement, that this tuple an, ln, and dn converge to the limiting tuple. It's only known in a few special cases. So for the matrix CRT maps that Liam talked about yesterday, under the harmonic embedding, it's known that these discrete geometries converge to Liouville quantum gravity. For the uniform random planar map, under the so-called Hardy embedding, that converges to the Brownian map, and also the matrix CRT map with a different embedding called a Smith embedding. This convergence is also known. Okay, it's a major open problem to prove that any natural, combinatorially natural, non-uniform random planar map converges in the scaling limit in this way. Okay, so we have this parameter gamma, and this parameter arises in the choice of random planar map. Roughly speaking, a larger value of gamma corresponds to a more fractal, a rougher kind of geometry. Okay, so when gamma is equal to √2, then the scaling limit of a random planar map, weighted by the number of spanning trees it has, this should converge to gamma Liouville quantum gravity with gamma is equal to √2. Uniform random planar map should converge to square root 8/3 LQG. Ising model decorated random planar map should converge to square root of 3 LQG. And the GFF decorated random planar map converges to the critical LQG gamma is equal to 2. So the increasing roughness you can see in the spring embedding, it just becomes more and more like a tree. The geometry becomes more and more singular as gamma increases. At the level of these area measures, when for smaller values of gamma, the counting measure of the vertices is more dispersed, it's closer to being uniform. But when your gamma value becomes larger, it becomes more singular, all the mass is bunched up in a few very small subsets of the unit disk. So in this way, you can see the increasing roughness of the surface in the simulations. Are there any questions? Okay. Yeah. So for the rest of today's talk, I want to discuss two different perspectives on Liouville quantum gravity. The first perspective is a conformal field theory perspective. And in this perspective, you have this Liouville CFT, and you want to solve for the correlation functions. The other perspective is more geometric. It's motivated by the perspective of LQG as being the scaling limit of random planar maps. In the setting, you get these random surfaces, and you have random curves on the surfaces, which arise from interfaces of statistical physics models. And it turns out that these two different perspectives describe the same random geometry, and that's the topic of today's lecture. Okay. So this is a slide that I don't really want to present because there's no way I get out of this looking good. But if you're not a physicist, a quantum field theory is a collection of numbers called correlation functions that arise as expectations of a random field. So, you're thinking of something like expected value of maybe, something along these lines, say, where phi is some concrete random field you can define. Yeah, this sentence is a bit contentious. Like, there are physicists who will tell you this is not really the case, but let's take this as a working definition. A conformal field theory is a quantum field theory which has conformal symmetries. And the one we want to focus on today is Liouville CFT, introduced by Polyakov in 1981 in the context of bosonic string theory. It's mathematically, this was constructed for various topologies, first for the sphere, then the disk, and so on and so forth. Okay, so we spoke about this briefly yesterday, but today I will use a blackboard and work out a version of the story for the disk. Let's see. So let's switch off the slides for a sec, for like 20 minutes. So we saw yesterday this Liouville action. Okay, so we're going to have a manifold. Let's say these are simply connected subset of the complex plane, and we put a smooth metric G on top of it. And so this is a manifold with the disk topology. We have some fixed gamma between 0 and 2, and we define this background charge Q to be gamma over 2 plus 2 over gamma. We also define cosmological constants. Mu and mu boundary. Let's say they're strictly positive. So what we saw in yesterday's talk is the Liouville action, which I'll write down here. So phi is a function from the to the real numbers. And the Liouville action is as follows. So the Liouville action has an integral over the bulk of the disk, where you have this Dirichlet energy, this integral of the squared gradient. You have this integral of the field times the Ricci scalar curvature. And you have this cosmological constant mu times e to the gamma times the field. And you're integrating over the bulk of the disk with respect to the volume measure induced by the metric G. You also have a boundary component. Again, you have this kind of curvature term, and you have this cosmological constant times exponential of the field, and integrated against the volume form on the boundary. I hope this is readable. Can people read this? Okay, good. So this is the Liouville action that we saw on Monday. I think it was discussed for closed manifolds on Monday, and I just added a boundary term. Okay.
Can I ask a question?
Yeah.
Is there some explanation for the boundary term? Because it's very close to the bulk term.
Yeah. I don't have a short explanation for the boundary term. It's, like you said, it's analogous to the bulk term. I can say a bit more about the form of this later. Yeah. So formally, we want to define these expectations of the field. There we go. So we take the expected value of f of the field, where f is some function. We use the angle brackets as is conventional in the physics. The subscript just keeps track of the things that we have chosen. I'm omitting the choice of gamma here. Gamma is fixed throughout. So here's a non-rigorous definition of correlation functions given the Liouville action. The expected value of f is going to be the integral over all choices of map phi from dr of f of phi times e to the minus the action times this term d phi, and this is some kind of formal Lebesgue measure on the space of functions. So what we're going to do now is we're going to find a way to make sense of this formal integral using the Gaussian field. Are there any questions? So the key idea is this. Okay, so even though we cannot make sense of this capital D phi, this formal Lebesgue measure of the space of functions, we can make sense of this weighted measure, where we weight by the exponential of the Dirichlet energy. Okay, and it turns out the correct way to interpret this, this infinite measure is as a law of the Gaussian free field. So we're going to let H be a Gaussian free field on your domain, and C is going to be a real number chosen from the Lebesgue measure on the real line. So this product measure over here describes an infinite measure on the set of pairs H comma C, and you simply add H and C. Okay? So this is natural in the sense that the Gaussian free field by itself, the free boundary Gaussian free field, is not the most natural object, because earlier we had to make this choice where we normalize, so it had mean 0 on the unit circle. If you don't want to make that choice, you can instead have the additive constant be chosen uniformly at random. And the only way to choose a real number uniformly at random is, of course, to sample from Lebesgue measure. Okay, so I didn't give a very strong motivation as to why this identification should hold. One way to do this is to look at the discrete setting and check that it makes sense there, where you can define, d phi on, let's say, if phi is a map from some finite graph to the real numbers. You can define the Lebesgue measure there, and then you can show that it makes sense as a Gaussian free field. But in the continuum, you just trust that this is a reasonable thing to do.
So what's the constant in front? The C?
Yes, thank you. The Z is going to be, yes, this is a log. No, there's no log. This constant Z is just going to be, it's just a constant in terms of the metric G, but explicitly is the zeta regularized determinant of the Laplacian operator to the negative half power. This isn't too important for the purposes of this talk, but it's just some explicit constant. Yeah. Okay. So this is really the only difficult thing here. Once you've made this definition, you can kind of just define everything else in terms of the Gaussian free field. So I'm going to write down a concrete thing with a simplified choice of the domain D and the metric G. Let's see. So, okay, so before that, we identify these integrals of e to the gamma times the free field as this GMC measure that we introduced earlier. And the same for the boundary term. This boundary integral of e to the gamma over 2 times phi is going to be the GMC on the boundary. The Gaussian multiplicative, Gaussian multiplicative chaos. I need another coffee. Okay, so for the purposes of this talk, as you'll see later on the slides, it doesn't really matter which choice of domain and metric you choose. So we're just going to make a choice now. We're going to choose the domain to be the unit disk. We're going to choose the simplest metric possible, which is just Euclidean metric on the unit disk. The Euclidean metric is flat in the bulk, and on the boundary it's a circle, right? It's got curvature 1. And so our Gaussian free field, we normalize it to have mean 0 on the unit circle. And so when we look at this term up here, the integral of q times the boundary curvature times the field, well, your field is now h plus c. H has average 0 on the unit circle, so this whole thing just collapses to q times the constant, times the real number c. And so now we can write down a definition for the correlation function rigorously. Okay, so now we have a rigorous definition for correlation functions in the disk for Liouville theory. Right? So the expected value of function f of the field is going to be this double integral where we take expectations with respect to the Gaussian free field, and we also integrate over all possible choices of the real number c. So it becomes a double integral. We just take f of h plus c. We have this exponential of your GMC in the bulk and your GMC on the boundary with the cosmological constants as coefficients. And you have this e to the minus qc and this constant, which doesn't really matter. Okay, and so starting with the Liouville action, using the Gaussian multiplicative, using the Gaussian free field, we can define the correlation function in a rigorous way. Not just at this level of physics. Rigor. Are there any questions?
Would you want to normalize it by the partition function or not really?
You could do that. You could divide by just 1. And if you want to do solvability theory, you could do that. Yeah. Yeah. For the purposes of this mini course, I think we generally will not want to do that. Yeah. Are there any other questions? Yeah, I kind of hand-waved over that. This is well defined for any f. Let's say f is to avoid issues with integrability, with integrals being oscillated, positive and negative, and having cancellations, we're just going to assume f is a non-negative function on some suitable space of generalized functions on the disk. So any space on which your Gaussian free field lives, you can choose that space. So I chose here the negative overlap space on the unit disk. You could just as well choose the space of distributions on the unit disk. That's fine too. So with this definition, this is now allowed to be infinity. And if you integrate some positive number and the integral is too big, you just get infinity.
Constant quantified for this finite, because you said you wanted to normalize, or this is not.
So it turns out that you will get, if you choose f to just be 1, you will get something finite. That's right. So for large values of c, this term will make everything very small. For very negative values of c, this will, no, you have to do something else, yeah. You have to add insertions to the field, which I'm going to talk about next. Yeah, and then these correlations will become finite. Yeah. Are there any other questions? Okay. Good. So if not, then let's go back to the slides. So given what we just discussed here, it's natural to make a definition of the following thought. So we're going to define something that I call the Liouville field on the unit disk. And it's exactly what he had earlier. He sampled from this 12th measure, where PD is the law of the GFF on the disk with mean 0 on the circle. And the C is coming from this e to the minus QC times the vague measure on the real line. The minus QC term, we had it just now. And so this product measure PD times this measure, you look at the field phi, which is H plus C. And that's going to be what we call the Liouville field. And we use this notation with LF sub D to be the law of the Liouville field. So it's just a Gaussian free field plus a constant from this e to the minus QC dc. Okay. So we can add insertions to the Liouville field. And formally what you would want to do is you take the Liouville field and you weight its law by e to the alpha times phi of z for some point z and some real number alpha. And that gives you this Liouville field with insertions. This is only a formal expression because phi of z does not make literal sense. Phi is not defined pointwise. So what you really need to do is some kind of regularization and renormalization procedure. So we replace phi with this regularized variant with radius epsilon. You put this renormalization term and you take a limit. So this allows you to rigorously define what you get when you weight your field by the exponential alpha phi of z. Okay. So it turns out that when you do this, your Liouville field is going to have a Gaussian free, it looks like a Gaussian free field plus an alpha log singularity at the point where you put the insertion. Okay, so for any point z in the disk and any insertion weight alpha, you can perturb your field by adding this alpha log singularity to it via this reweighting, and this is called adding an insertion to the field. So given that, we can define the correlation functions as follows. So exactly as we wrote on the board earlier, we want to take, when you define correlation functions, you want to weight by this exponential of the GMCs in the bulk and the boundary. And then formally with this alpha phi e valued at 0, that's the same as adding an alpha size insertion at the origin. So this allows us to define the one-point correlation function on the disk via this integral. So I dropped the partition function of the free field because that doesn't matter for our purposes. But this is a rigorous definition you can make. Okay, so starting with the Liouville action, we can end up with this definition for the one-point correlation function. So this is a quantity which, it is defined to be the Laplace transform of the GMC area and GMC boundary length of your random field. So Laplace transforms encode the joint law of these observables. So the correlation function gives the same information as the joint law of the area and boundary length. Okay. You can also define, we made a definition for the disk, but you can define it for other manifolds. So for the sphere, you can define a 3-point function. In the same way, you define the Liouville field with insertions on the sphere, and then you just weight by the exponential of the GMC, and that defines correlation functions on the sphere. Okay, so the goal in CFTs is to compute all of the correlation functions. So for every choice of manifold, you want to be able to write out an expression for the correlation function. And on Friday, I'll say more about exactly what has been done for Liouville theory. Are there any questions so far? Okay. So we're not going to use these properties, but it's maybe good to just state a few of these. Why do we say that it's a conformal field theory? Because it satisfies the source property. I wrote this in a rush, so if there's a mistake, please point it out. Okay, so Anki spoke about some axioms or properties that you expect CFTs to satisfy, and these are two of them. The first is that it doesn't matter. I guess it's almost tautological, right? But if you have a diffeomorphism from a manifold to another manifold, then the correlation functions should be the same. The second one's more interesting. You perturb the geometry. So if you have a manifold with metric G, and you perturb it by adding this e to the 2 sigma term to make the metric bigger and smaller in various places, then what does that do to your correlation function? Well, there's an explicit formula for that. The ratio of the correlation functions is just going to be given by the ratio of the free field partition functions to the power of 1 plus 6q squared. And it's, this quantity in the exponent here is the central charge. And this could be said to be the defining property of the central charge from the perspective of correlation functions.
So the ratio doesn't depend on F?
It doesn't depend on F, yeah. It's yeah, you can view it as being something like, you can think of F as being something like the total GMC area, and then this is like the coordinate change formula that when you change from one domain to another domain, and then the GMC area is at the same, regardless of your choice of parametrization. If there's no questions, I'll move on. Okay, so that's the first perspective on Liouville theory. That is a conformal field theory, meaning that you can define these correlation functions, and we'll see on Friday you can compute the correlation functions. So due to the rich algebraic structure and integrability of Liouville theory, you can compute all of the correlation functions, and that means you can compute all of these observables. For the disk with 1 point, you know the joint law of the area and the boundary length. For the sphere with 3 points, you know the law of the area, that sort of thing. So the definition is in terms of there's a geometric perspective. where the correlation functions give you information on the geometry. The second perspective I want to discuss today is the random surface perspective, and this is the one motivated by viewing Liouville quantum gravity as a scaling limit of random planar maps. Okay, let's see. So we have 10 minutes, so let's see. So earlier today I talked about how when you embed a random planar map in the unit list, and you take a scaling limit, the resulting geometry is Liouville quantum gravity. And I gave a specific choice of embedding, but of course, the choice of embedding isn't necessarily fixed. These two embeddings I've drawn here differ only by rotation. Both of them are equally valid. So how do we choose? We want to say that these two have the same geometry, even if I drew them on the disk in a different way. And so when we define the notion of a random surface, we want to, quote unquote, mod out by the choice of conformal embedding. And that's what we're going to make precise here. So we already know that once you have a domain and a Gaussian free field on it, that describes a geometry. You've got this area measure coming from the GMC, this boundary length measure, etc. And so now what I want to do is to say, these two domain field pairs, DH and D tilde H tilde, these describe the same geometry. When is that the case? You can define this equivalence relation between pairs DH and D tilde H tilde if they satisfy this relationship. So you want H to be equal to H tilde, composed with a conformal map plus Q times log of the conformal map's derivative. It's not obvious at first glance why this is the correct notion of equivalence class, but the reason is simply because this is precisely the relation for which your LQG area and boundary measures agree. So if I take my GMC on the left picture, and I take the GMC on the right picture, then they agree after this conformal map F, if and only if the fields H and H tilde satisfy this relationship. So this is analogous to it's something like when you do if you have W is Fz and you define this, then the area measure, dz becomes the area measure of F. You have to put some kind of F times Z squared term when you do a change of variables. And this 2 is going to be replaced by Q. That's essentially what this Q log F prime term is doing. Okay, so because what we care about is these LQG observables, these GMC observables, so we want to define a quantum surface to be an equivalence class of pairs D, H, where we're modeling out by pairs which satisfy this identity. Okay, so any two members of the same equivalence class have the same observables, so we think of them as the same thing. Okay, and the remaining time we have left, I'm going to discuss some special surfaces. So the first special surface that I want to talk about is a quantum sphere, or LQG sphere. So we're going to take gamma squared 8/3 for now. This corresponds in the discrete to the setting of uniform random planar maps. So I just choose uniformly at random from the set of all planar maps with n faces, and I send n to infinity. So let Sn be the set of planar maps with n faces. And I didn't say what kind of planar map. Earlier today, the picture I had triangulations, but you could also have quadrangulations or bipartite planar maps, etc. It turns out that for a lot of these different models of maps, the enumeration comes up to the same thing. You have some non-universal constant in front. You've got this exponential term, which is also non-universal. But this power law here is universal. It doesn't matter if you choose triangulations or quadrangulations or anything. You always get this n to the minus 7 over 2 term. So this is kind of a weird story, right? Like when you talk about how big is an elephant, you look at the first, 4,000 pounds instead of like 4,005, and you keep the 5 and you throw the 4,000. I don't actually know how heavy an elephant is, but that's the analog here, right? This is the biggest term. This is the one that really matters, but this is a universal term, the lower order one. Okay, so when we define a random surface, we want to strip away the non-universal terms. How do we do this? The first way is we can just fix n. Then all of these things don't matter anymore. That just gives us a probability measure on the set of, you look at a probability measure on the set of n face planar maps. You take a limit, and then use a probability measure on Liouville quantum gravity surfaces called the unit area quantum sphere. Okay, so this object here corresponds to a probability measure. The second perspective, the second approach is we can simply weight every planar map by this quantity. Okay, so you have this infinite collection of all planar maps. You take this union over all n, but you assign each map this Boltzmann weight. And in the scaling limit, this is going to give you something called a free area quantum sphere. Okay, so this is an infinite measure. If you condition on the area to be 1, that gives you this finite probability measure. Okay, and so here's the story. There is a way to define a Liouville quantum gravity surface with GMC area equal to 1, and more generally equal to A. And that's going to be a probability measure, denoted by this symbol in the corner. So you can always define this measure starting with the Gaussian free field and doing things to it. Now, starting with this probability measure QSA, you can define a non-probability measure by adding this power law term to it. So this is analogous in the previous slide to this n to the minus 7 over 2. N is the area of your map, and you're weighting by the area to minus 7 halves. Here, it's the same thing, except that gamma is not necessarily root 8/3. So this is not necessarily negative 7 halves. Okay, and so that lets you define this infinite measure called QS. Okay, I didn't actually give a definition of QSA with the whatever that symbol is, but it can be done, and I'll give a description next time. Okay, are there any questions about this? Okay, let's see. I'm trying to decide if we should press on or if I should succumb to the heat and just end the lecture 5 minutes early.
So just, does the QSA sharp already satisfy this transformation law that you have, or only the QS?
Yeah, so let's see. So a sample from QSA sharp is going to be one of these equivalence classes.
Okay, so this is already something that is there.
Yeah, that's right.
Okay.
That's right. Yeah.
So what's the advantage of the QS?
That's a really good question. The advantage of the QS over the QSA sharp is that the QS has a correct partition function. So later on, we're going to be doing things like cutting and gluing surfaces. And once we're in that setting, we really will want the partition functions to be correct, so the identities are natural. I'll just write down one example now, which we'll discuss in more detail next time. So on the left-hand side, I'm going to have a surface with a sphere topology together with a loop on top of it. And precisely, it's going to be one of these QS surfaces, quantum spheres, with with an SLE loop on top of it. So this is the infinite measure with the power law for the area that we wrote down earlier. Now we want to cut. And that's going to give us a pair of surfaces with the disk topology. And it turns out that this pair of surfaces, the law is going to be something like this. You integrate over all possible boundary lengths of the disk, and then you have this quantum disk with boundary length L for the first one, followed with quantum disk with boundary length L for the second one. And then you also have a further term L, which is corresponding to the number of ways of gluing these two things together. Intuitively, if you have boundary length L, you have, if you this Way-Peterson like notion of volume, like you have this DL, like different rotations. Yeah. So the reason I spent that time setting up this notion of a non-probability measure is because these things, which come with their partition functions and everything, are most natural from this perspective. You can cut and glue. Yeah, I'll say more about this next time. Yeah. Are there any other questions?
Yeah, this is multiplied by L by the length on the left.
Yes, that's right. So this is a measure, this is another measure, and this is a real number. Yeah, and then you integrate over all possible choices of L. Yeah. In the discrete, it's something like if you have two planar maps with boundary length 5, then the number of ways to glue them together to get a sphere is 5. It's because you have 5 different ways of rotating them. Yeah. Are there any other questions? Okay. Good. So I should stop here. I should mention one more thing, just that all of this stuff is motivated by random planar maps, and you can write down the correct identities using that perspective quite easily, but none of the proofs go through random planar maps. As I mentioned earlier, proving that planar maps scale, converge to Liouville quantum gravity is highly non-trivial. These things, yeah, I don't know of any result of this type that you prove using planar maps. Are there